That's good. One thing. All right. All right. Okay, so we're going to talk some more about this scale-free network stuff. And so scale-free networks, and then we're going to go into contagion. Extremely, incredibly interesting. I mean, all of these things are interesting and important, as you know. But contagion, really huge. So we'll have some biological contagion stuff. We'll have, some basics there. Some kind of insights about what goes wrong when you extend the model a little bit. Some of the models we've already seen, we'll be using those again, kind of hierarchical structures. Then we'll move on to social contagion, whole new bag of things there. We've moved in, only in the last really few years have we gotten to the point where it's moved beyond models and ideas, which are incredibly important, right, because they help us kind of figure out what's possible and what the stories of real contagions might be. And there's your intuition, which only goes so far, unfortunately, right? And then there are models that we make, and they have surprising behaviors, which we can eventually understand. That's very important. But then we're getting to some real-world data now. It's still very messy, right? We're able to record things, but we're getting somewhere with that. So there's some controversy about how things spread socially still in terms of measurement and so on. So after that, we get to scaling. That's going to be a great, there'll be theories that kill each other. Theories that disappear to Buenos Aires. There'll be a theme there. And surprisingly reappear later on. So it's going to be a lot of fun for me. Anyway, but I think you'll like it. So scaling, very, very important. All right, so let me see where we were up to. Come on, thing. Yes. So we're going to do a little bit of analysis, just a little bit here. Won't put all the details in. In principle, they would be in an assignment, but we'll see how that goes. I don't want the team to explode. Okay, so we worked through this a little bit, and we got the same result as Barabasi Albert, right? So this is this derivation that's different to Simon's model, where we had this tunable exponent pop out based on a function of innovation rate, right? New words appearing, new cities appearing. So this is all about networks. Thanks. And the thing we're changing here is this attachment kernel. That's what we're going to change. So if you just have this linear attachment kernel, which we gave a great argument for as being a very reasonable, natural thing, right? So you join into a network, and then you connect to some of the friends of this node you're connected to, maybe some other nodes you connect to. It gives rise to a preferential attachment kernel that works with a pure linear attachment. Right. Words. K. Right. Okay. This guy. AK equals K with nu equals 1. So a couple of ways we can change this, and this is what we'll explore in the last few slides here. Nu not equal to 1. And we talked about this. So if it's greater than 1, it's a much richer gets richer problem. And K less than 1, they get a little bit richer. All right. But we can also do this. We can say, all right, well, let's have this K, and we'll just play around with that a little bit. So it's still linear attachment because we see that happens in the real world. We can have an argument for it. Let's just tweak it a little bit. So a few things that we want to do as we go forward with this analysis, and I mentioned this the other day, but the idea is we're going to change. So there's going to be a linear attachment kernel. This is AK, right? And this is really discrete, 1, 2, 3. So it's these weights like this. And then we'll have a value alpha at this for attaching to guys with one friend. Okay? And we'll tune this one up and down. But everything else stays the same. So that's all we do. Very simple change, tiny change. So this is about whether you, so it's rich gets richer, plus you have some, you want to help the people with one friend, right? So you're helping the world. I mean, I do think maybe we could frame all of this as these are natural Ponzi schemes, right? All these parallel size distributions are somehow manifestations of the Ponzi scheme. So, Bernie Madoff is sort of God in some way, right? He's just enacting what happens naturally. All right, so now we might have a more complicated thing where we know we have this that it's going to grow linearly. So we're not changing it crazily. We're not going to do anything like this. So we still have to figure out, we still have to normalize this. We had this story before that because we're only adding one link every time, then we know that we have, if we add up all of these degrees, right? If we add up all the degrees in the network, then it's going to be 2 times t, right? So every link that appears, there's one link per unit time. Every link has 2 ends to it. Okay, so that's going to change. It was 2t before, so we make this assumption that maybe it's not 2 now, right? So it's not going to be 2. We're adding things in a bit of a different way. We're going to have a mu t. Right? Things are going to grow in a slightly different way. Yeah, we could do it really well before, but this is it's just going to be a more complicated business. We're not sure how to add these things up because we have to do this. We have to add up all the, so we find all of the nodes that have degree k prime, and then we multiply them by their weights. And if this is a weird weight, right, it's not just simply k, this is a weird weight, then it's going to be harder to figure out how to do that. All right, so what we assume, though, is that it's going to grow as mu t, and we have to figure out this mu later on. It's still going to grow linearly. That's a nice thing. So we do everything as we did before. I'm going to leave out details. But we also assume this, that eventually it stabilizes, right? So the number of nodes with degree k at time t is really just going to be some factor times t. The whole distribution is growing linearly. Exciting. All right. So we had this kind of story before. You can go back a few slides, but we ended up with this difference equation, right? This is for the node that the new guy that's appearing and making one link. This is how the classes change probabilistically. The normalization here was 1 over 2t, so that's to make these things into probabilities. Now it's 1 over mu t, so this is the change. This is all we get, right? There's a mu sitting here. So we can do the same kind of analysis, right? Same thing as we did before. We're going to put the nk on this side, all of the nks on this side, and all of the nk minus 1s on that side. There's just this piece ends up over here. There's a mu, so we'll multiply this over here. We'll get a mu nk, so that's this beast. And we have an ak nk, and that's going to pop over here, and we'll put it out in front. So there's a delta k1 here and a mu delta k1 here. All right, good. So that's all there. So this is a difference equation, and in principle, we can figure out how this thing works. It's not as nice and beautiful as before. We had these, well, in principle, you would go through it in an assignment, but we have factorials and things appearing. So very simple when we're at k equals 1, right? So k equals 1, there are none of these guys. N0 doesn't make any sense. This piece is a Kronecker delta, so this is just mu. And we're looking for n1. So we end up with, and this is k equals 1, so we end up with n1 is mu over mu plus a1. So we put this blob down here. And in general, we have this recursion relation here, because when k is greater than 1, this is a 0. It's a Kronecker delta function, right? There's no injection there. Then we have just a nice iterative thing. So we have to think about this guy. Now it's got these horrible AKs in it, right? So these things could be anything. You could prescribe anything here. And one we'll try to do is we'll have a very simple k. AK will equal k, going up from 2, but it'll be different for A1. That'll be alpha. Exciting. Right, so we're going to, I'm just going to tell you how this works out. And in principle, there's a question here, right? So, so if we have this kind of behavior in general, so if AK is growing as k, right? So it's still a linear attachment kernel. So you would think it should still give you the same kind of behavior, right? The big guys are still getting the same deal, but there's something is definitely happening. If you inflate this a long way up, then there's really a lot of tendency to connect to these individuals that have one friend, right? So it messes the Ponzi scheme up. Right? These are the ones who should join later on. If you have one friend, then you've been bought into this thing and you think you're going to make lots of money, but you don't in the normal one. So the details matter in horrible ways, but essentially you end up with this product. You have to do, right, because we have this iterative story. Right, we go from n1 up to n2, n3, and we can build out this story. It's a product of all of these kinds of pieces. All of these funny little guys are here. You can figure out this decays now as k minus mu minus 1. Right? So mu was 2 for our simple case, the linear case, and that gives us back the Barabasi-Albert model, and we get k minus 3, right? K to the power of minus 3. So we have to figure out, we made this assumption that the sum of all the degrees was scaling as, the sum of all the weights, I should say, is scaling as mu times t. So we have to figure out what that is and see that it's consistent. So you can do that I'll show you that. So we need to find mu in principle. So again, it's exactly this expression. So we're assuming this is true. We have to see that it makes sense now that we've got some form for this distribution. We know it's growing like this, so we have this result, right? So mu t is all of that blob. So mu is just equal to the sum of these little nks times these weights, whatever they are. So we have this expression for little nk. We're going to stick it in. It's from the previous slide, so I know going through this somewhat fast, but we end up with this expression. We have mu is equal to this whole blob here. There's a mu sitting in here, right? We have this product that goes up to k, and then k goes from 1 to infinity. So it's a nasty thing. A fun-looking thing, but a bit nasty. All right. So it is a closed-form expression for mu. Some of these beasts disappear, so these things are going to disappear. That's pretty good. These mu's will disappear, right? They're sitting there. They're just healthily sitting there in the whole thing. So in fact, there's just this one mu sitting down here. So in principle, we can solve for mu, right? Now we roll out, we get a computer, and we do some funny things if we allow for very arbitrary a sub j's here. Okay, so we can solve for it in some very special cases analytically. We do that for fun because we want to find something out. But in principle, it looks like it's good, right? That this thing will grow linearly. The sum of all of the weights as a function of, because it depends what's happened. So your network is evolving. You have some degree 1 guys, degree 2 guys, degree 3 guys, degree 4 guys. You have to sum up all of the weights and then divide through to get your probability of attachment, right? So that's hard. Again, we talked about the other day, it's a very hard thing cognitively to do. And the one that makes sense from a sort of an easy cognitive or easy kind of process way is the one where you just attach to someone randomly and then attach to some of their friends, and that gives you the linear attachment kernel. So this is burdensome, but it's explorable. We're interested in this property of universality, robustness of the mechanism, and we get some funny things. So here's the one I've been telling you about. So let's put in A1 equals alpha, and then everything else is simple. Again, you have this story that the exponent is mu plus 1, and we have to find mu. And in fact, you can find it, right? So it turns out you get this expression for mu. So the mu over alpha, these gamma functions. We love gamma functions. They appear all the time. I know you don't. But it's a sum of these things. I'm not going to give myself. But so you could turn these into beta functions, whatever you like. But it's a sum of these horrible things. And in fact, you can actually solve this. And you get this rather simple little thing. So mu times mu minus 1 is equal to 2 alpha. And alpha, again, is the weight for the node 1 guys, right? So this is a scheme where it scales as your degree, except right? It's a government intervention, and you're trying to help the ones with 1 friend, right? That's what you're doing. You're trying to get them in at the start. Once they've got 2 friends, they're off by themselves. But you can think of it like that. In fact, you get this. So you get mu is this business here. Alpha is sitting in here, so we can get back to when we put alpha equals 1. This should work out, right? So 1 plus 8, square root of that is 3. 1 plus 3 over 2, so we get 2. So we pop back to 2, mu equals 2. So that's, magic, obviously. It has a magical feeling to it. But you can tune alpha anywhere. Any sensible thing, of course, is to go between 0 and infinity. So 0 means, you're burning everyone you're making it worse for them. If it's less than 1, you're being nasty. And then above that, you're trying to help. And so in general, if gamma is mu plus 1, that was our general result for this power law that pops out. We're getting a nice power law. Then if we range between 0 and infinity, then we go between 2 and infinity for gamma. So we can get just this very simple tweak of the model, this tweak here, we can suddenly get every exponent we want. Right? This is an example where it's ridiculous. We go through an analytic thing. This may never happen, but it's very useful to have a concrete thing where everything can be sorted out. We're not just simulating or so on. That's OK. So obviously, as you move away to more complicated attachment kernels, you have to do simulations. You have to do other things. But now we have this understanding of, for these things that look linear, right? Things that look linear like this, it can go all over the place. Again, it's very different to Simon's model. Simon's model, you had this innovation rate. That's not in this. In this model, 1 node is turning up every time, and they're attaching. And so it doesn't quite have that story. Craziness is the summary. was a funny noise. Okay. So 2 more pieces to add to this. So let's look at non-linear attachment kernels. And I'll just give you the results for these things. Just show you how bananas it can be. On a scale of 1 to 5 bananas, it's 5. So we have A, K is growing like K to the nu. Now we're going to go below 1, all right? So that's a somewhat, the rich get somewhat richer. It's better to be richer than the other guy, but you're not getting as much benefit, relatively, as compared to the linear one. So it turns out you get this. You get these kind of stretched exponential stories, and they're truncated power laws. So the k to the minus nu, they're actually k to the minus nu, that pops in, right? So that's a very different looking thing. And then e to these, the correction terms in here, but there's this piece in here, so that when k gets large enough, this exponential tends to wipe things out. So there's a power law with an end to it, right? Which we see a lot in many physical systems. We see that same sort of, right, power law gets crunched. I've called them Weibull distributions. Maybe I've got a little excited about that, but they're all in sort of this class of things. So now in fact, the details of the kernel don't matter. So you can show that, right? You can this kind of little aberrations we put in here, which you think shouldn't do anything. This should be, maybe it should have some effect if you make it really large, but it turns out any variation from 1 here, any variation moves the exponent. It fundamentally changes the universality class. Right? You just tweak this a tiny bit, and you're in a, it changes the universality class a little bit, but it does. Here now it's robust, right? You can, as long as it looks like a, maybe it's a k to the half, you always get this form coming out. If you mess around with it, it's robust. So we get a different story. So that's weird. That's just weird. All of this is weird. So we get this universal story for the degree distribution, provided nu is smaller than 1. There isn't this fragility to the mechanism. Does that make sense, right? So when we have nu equals 1, we have this fragility. You can mess around with it in microscopic ways that change the whole thing. Here, as long as it's less than 1, it's a robust thing. You can tweak things. So there are all these results, right? So if it's between a half and 1, then you get this form. If it's between, and there's correction terms between a third and a half, you get this form. And in general, between, right? So yeah. So they went to town. This is what happens if you like math. You go exploring. So they went exploring, and they solved the whole thing, plus correction terms. All right. So they have a whole story. But yeah, okay, pretty great. So if we get rich gets much richer, nu greater than 1, now we get to a winner-take-all mechanism. So you move just above an exponent of 1, right? Now it's winner takes all. And that's so that's a very different story. So whoever's in, well, it's a bit subtle. Whoever gets in front after some point, and if you saw the talk yesterday, there was some from Yuru, we had some. She talked a little bit about hashtags taking off, right? Big Bird and Save Big Bird and so on is from the debates. And they had some nice evidence that, I can't remember which one took off first, but maybe it was hashtag Big Bird and so there was some, right, and some back and forth actually over even 48 hours, 72 hours as to which hashtag won. And they were really, they were very big hashtags. They're also accounts, right? Accounts get started and they get followed, right? Like empty chair and so on. That's a good game that people like to create. I mean, from every spectrum, every position in the spectrum. Well, I guess the kind of ends of the spectrum. All right, so that doesn't always happen, right? That the first mover, there's a first mover advantage, which we've talked about. At some point, once there's a big enough gap, you can show that that's it, right? That the one who's in front will now win, and we have a monopoly type story. Right? And what happens is one single node is basically ends up being connected to most of the others. So it's really a big star network. So that's a pretty big change, right? If you go above linear, superlinear attachment kernel, then it's a very different result. So that's a kind of a fragility. If you go below linear, you still have a power law, but it's truncated. So that doesn't feel as harsh, right? That's not as bad. It's truncated, but it's not as bad. This is now just a different thing, right? We basically get a delta function for the node that's connected to everyone else, and all the others have some tiny little number of friends. So the world is a little messed up. If nu is in fact greater than 2, I don't think it's equal, but greater than 2, then the node that gets in front just crushes everyone, right? So it's in fact, out of the whole network, almost everyone is connected. It's actually, you know, if you let it run for an infinite amount of time, then you end up with just really a finite number that are hanging off by themselves, so early on. So it becomes very extreme. So even just that. So if you have if you figure out that your mechanism, that's, you know, the thing that you're watching is growing, you have some ecology of things that are accumulating in some way, and there's somehow a rich gets richer mechanism that has a power of 2 or more, then it's really extreme. And in fact, you know, you probably won't observe any other any other team members except the one that dominates. So that can happen potentially in compartments of a bigger system, right? There's one that wins over here and one that wins over here, and then they somehow start to fight with each other. So, all right, nutshell for this guy of sorts. And this is really about for models of networks. So that's what all of these slides were about. Obviously you have graph theory coming before it. But we're, in looking at what's now viewed as this field of complex networks, that's the tag for it, which has really matured into something solid in the last 15 years. It's more about the dynamics, right? How do these things come into being? You know, that wasn't true for the small world network, but that's, in this whole scale-free thing, that's what we're after. Lots of stat mech and an enormous amount of, that kind of behavior. So obviously, there's been a lot of work in describing and explaining, and this is sort of, to me, this is science, right? So, and I find it kind of ridiculous to have to say, but it's describe and explain, and so a lot of work has gone into this, and it's still going. You know, it's hard to, as I said, it's hard to describe the internet. It's hard to describe where it is now. It remains hard to describe social networks, but we obviously have much more insight into them with things like Twitter and so on, which is not everything. Explanation, micro to macro features. When we can do that, and these have been beautiful examples, right? The scale-free network one has been a beautiful example of that. This microscopic interactions and so on that are giving rise to macro features. Love it. Few things that we really understand: degree distribution, clustering, assortativity. These have popped up. So modularity, group structure, overall structure. Those things have. There's a little bit of history in how they've come to be important, seen to be important. People copy each other, right? So clustering was one of the early things talked about. So that appears in everyone's paper afterwards, and so we've had some, so still, as I said, still a lot of work to be done in terms of sorting this out. But we have this idea that degree distribution is kind of a big thing, number one, right? In some sense, overall structure, I would say, is this modularity piece, which is something I talk about a lot more in the next course, complex networks, but that is, that's huge. We've spent, again, 10, 15 years figuring out better and better algorithms, which are now built into some of the nice visualization software out there of how to detect structure in something that has 100,000 nodes. There's still a big messy network, but if you tease it apart, you can start to see some modular structure. So that, in some ways, these are the two big pieces, but all of these things can have dramatic effects, right? If you tune them up and down, they can change how processes work on these networks. All right, so that's good. There's all the good stuff at the end. I could add more to that too. And that is a screaming weasel. Okay. Fight the good fight, weasel. Poor little guy. Sorry. Okay, so I'm going to talk about biological contagion. There's sort of an intro to this, and then I want to speak specifically more about disease spreading. Obviously, this is the overview of networks in a way, and networks appear in all the things we talk about. Most of the things I'll talk about from now on, it's a big deal. It will turn up in scaling too, actually. So, all right. Well, it's kind of a aliasing problem, right? So I put this at the front of all of my slides now because I like them. Okay, so this guy often finds himself in very strange places when the oldest one comes home from school. He's usually trying to find penguins somewhere. There's like some sign that says penguins inside and he gets stuck. So that's an amusing game that someone plays. Anyway, Lammy is a more benign character. He has sort of a malevolence, right? So there's a whole story of tofu penguins, and yeah, but clearly he's not towing the line. Anyway, so good guy. Right, kind of like cats, right? Cats are sort of sociopaths that are waiting for you to die or something. They're making all this calculus. Dogs are like, you're my buddy. Yeah. The seal, I think, is in the cat category. All right. At least in our imagination. Okay, so we're going to give you some background. Talk a little bit about prediction. That's a big problem here, right? So, is this disease going to take over the world? You know, and what's the chance that such a disease will come along? I'll talk about how messy this is. There are some fantastic models out there. They range in from the simplest ones, which we'll talk about. We necessarily have to talk about, and then there are these amazingly complicated ones that are becoming more and more sophisticated, which involve, of course, knowledge of everything that we have. So airline networks, demographics, local mobility, transportation, and so on. So there's a game where you essentially, with these, you can simulate these things. You drop a horrible disease into, you throw Ebola into Paris and see what happens. So it's good for people who are, stroking white cats and on swivel chairs. Don't get out much, right? They can simulate, also governments. All right, so can be the same thing. So let's see. So yeah, wow, good. So maybe some of this is getting dated. You probably remember this thing, but I mean, I'm eternally right. So contagion, right? It's a good word. Is it right to think of these things that have spread tremendously? Is it right to think of them in the same way as we think about diseases? And how do we think about diseases, right? So lots of different diseases. The Da Vinci Code, that was a horrible kind of virus. So Sudoku was a good example. That spread off. These are just some recent things, and they take over, or Justin Bieber takes over. What is going on with that? If anyone needs to apologize, they can right now. So language, what about that? Language spreads, right? And elements of language spread as well. I mean, we have abundant examples now that we can really get into. Of course, you can trace things back through written literature for thousands of years. You can see how things changed and how they evolved. We've talked a little bit about that. With Twitter, you can see the usage of particular ways of framing things. Obviously hashtags, but even just the hashtag, right? So that's invented by someone at some point and copied, and that becomes a way of doing things. And retweet was again, just invented by someone, and eventually it becomes codified. But there are actually little, you can see local dialects for Twitter, actually regional ones where people have little usages, Pittsburgh or so on, they'll have a little, Pittsburgh has some funny words. Yinsburg. My wife is from it, so I know about these places. So places do develop their own little, even Twitter accents, and so you can study those things. How do things spread? Religion, right? There's some efforts to make it spread, stop it spread. Some are lazy religions, some are very proactive. Democracy, right? That's been a, thing to spread recently. Is it contagious? I don't know. So we have these, what I call naturalmorphisms, where, right, the feeling was contagious. People talk about many things as spreading like diseases in some way, right? Or bushfires, right? You spread like wildfire, that's a good one. There's a strong statement. This is a while back, right? Freedom is the most, it's still relevant, obviously, the most contagious virus known to man. Interesting. I don't know, strong. We like this word. Nothing is so contagious. I don't know, actually. If you're too enthusiastic, people probably try to, that's Australia. Yeah, they'll put a handbrake on you. Anyway, that's just, there are these ideas. This is Ambrose Bierce, you may know of. And so the doctrine that everything is beautiful, including what is ugly, everything good, especially the bad, and everything right that is wrong. So optimism, it's hereditary, but fortunately not contagious, right? I don't know. Do you know the Devil's Dictionary? Some of you may know this thing. Yes, maybe. None of you know it. Famous American guy, right? Who disappeared very strangely, apparently. I don't know. Anyway, but he wrote this kind of somewhat obnoxious, amusing dictionary with good definitions in it. So I'll give you a few of these things. So Eric Hoffer. So this is a funny guy. So this fellow was a stevedore and wrote these books that were full of sort of aphorisms. And this is really, after the Second World War and the Cold War and all this sort of stuff was going on, and worried about the world being taken over by sort of tyranny and so on, right? That was the concern. So he has some interesting things. So here's his line. So there's a grandeur in the uniformity of the mass, right? A fashion, a dance, a song, a slogan. This is maybe from the 50s or a joke. Sweeps like wildfire, so we love it. From one end of the continent to the other, and 100 million people roar with laughter, their bodies in unison. He was good at writing these things. Hum one song or break forth in anger and denunciation. There's an overpowering feeling that in this country we have come nearer to brotherhood of man than ever before, right? And it happens. It happens only really in extreme circumstances, like American Idol or something like that. But war, of course, and so on, right? Other things. So interesting fellow, as I said. So he wrote a number of these books, and they're just sort of. He's not a scientist, so you may some people won't like it, I suppose, but. But he popped these books out, Thoughts on the Nature of Mass Movement. So he's working on the dock in San Francisco. Stevedore. He has these great quotes, right? We can be absolutely certain only about things we do not understand. Mass movements can rise and spread without belief in a God, but never without belief in a devil. Where freedom is real, equality is the passion of the masses. Where equality is real, freedom is the passion of a small minority. That's good. Anyway, had a lot of fun. And some of his stuff got made into these despair.com, the motivational posters. There are the obvious, this has been around for a long time, but there are the anti ones. So when people are free to do as they please, they usually imitate each other, which is going to be a big deal for our social contagion story. Never underestimate the power of stupid people in large groups. Also good. Yeah. Okay. Sort of a side note, you should look up, if you don't know, you should look up the Dunningkruger phenomenon. That's an important thing. All right, so what it is I should say, so what it is, I shouldn't just do that. There's a study at Cornell. It's based on people doing some writing and evaluating each other's writing, right? And you had to also evaluate yourself before and after and this whole business. So the finding was kind of a meta-incompetence story, right? So people who were didn't rate so well, through various measures, tended to rate themselves highly, and then after seeing other people's work, continued to rate themselves highly, and then people who were further up, near the top, kind of maybe lowballed themselves a little bit, and then moved their estimates up a little afterwards. But it was this inability to see that you don't have ability. So whenever I think about that, I think, yeah, people are stupid, very funny, right? They don't know what they're doing. And then I think about it for a little more. And then you get a terrible feeling about yourself. And because it's all about, self-confidence. And then you forget about it. And you go back to what you're doing. You pretend you forgot. So you can forget about it. OK. But it is, yeah, good. All right. So there's just a little bit at the start. And I'll have some more pieces. So should I add? Yeah, I have more pieces. So definitions. All right, so it's we'll be interested mostly, but not completely, in the spreading of whatever it is, an entity between individuals in a population, from individual to individual. So it's viral marketing, if you like. Right? You want, if it's it's word of mouth type stuff. Of course, disease. You sneeze on someone, and of course, contagion. This word contagion can mean that, or it can mean the disease itself. Yeah, that's a pretty obscure reference, the dreaded lurgy. Okay, so it's pre-Monty Python. Yeah. Okay, it's there. Okay, so it's a good word. All these words are good. So con, together, and to touch. So contagion really is about that. I mean, we can mean it to mean whatever we want, but it does have built into it this. It's the touching story, right? So it has this, contagion has sort of a negative story to it. I mean, it feels pretty bad, which is good. It excites the public. Spreading might be a more neutral word. And in some ways, that's what the study of contagion in general is the extension of, right? So the simplest kind of spreading is diffusion. It's very benign. Things are just spreading out. That's good. That's a very basic physical kind of spreading. And we can start to think about spreading on networks and all sorts of other stuff. But it's an exciting word. So we'll use this word. There's been a few big books. There's a book by Jonah Berger that's just come out recently called Contagious, right? So he's a professor at Wharton. He's done a lot of interesting work. Has some stuff that just came out about people sharing New York Times articles. So there's that little. Does anyone ever share? And this is not the way to sample things, but from you younger people, does anyone ever click on something, say email to a friend? Like on a website, right? Do you ever visit such websites? Right. So the New York Times has this. If you want to email this story to someone, a lot of places have this. I don't know why they still do it, but there's tweet and all these things. But there is, email it to a friend, right? Anyway, so that's some subsample of the population that reads the New York Times and clicks on those things. And if you look at what people share, that's pretty easy to just even look at it. You'll see it. People don't share bad things. They don't share stories about wars or anything, because that's just not good. They read about it, but they don't share it. So they share things about health and about dogs and cats and things that make people anxious, though. I mean, some of the big disease-spreading stuff. As long as we're not, in some survival mode and we're, in a bunker somewhere, it's like away from that possibility right now. Then people are happy to share some information about that sort of thing. So he has a whole, body of work on that. He's also done baby names, so baby names that take off very fast, disappear very fast as well. So that's an interesting aspect, and so that build up connects with the drop off, which is connected to the endogenous growth thing that we've seen in other areas, and we have some work on that. Right. So, all right. I don't know can I get that to work? Oh yeah. Wow. That's just terrible. Wow. Why would you do that to me? Let's see if I can find the... you bad thing. Okay, let's do that. Let's get... I think I can do it. It likes to ask these things, doesn't it? Yeah, there you go. All right, so this is a spreading of something in the US. The colors, the colors are news stores, right? So it's blue, and then the red are the news stores. Can you see this okay? So this is pretty old school 2D spreading, right? I mean, when you go back in time, you've got some plague spreading and so on. There were carts and, yeah, there you go, it's Walmart. Let's play it again because it's great. So Arkansas, right? Yeah, and it's based on trucking lines and so on and being able to get things to places. And it really doesn't, yeah, they built the infrastructure. That's where people live. Vermont apparently was the last. But did receive one. Okay, that's not good. Okay. I'll make that thing work. I don't know why that didn't work. So that is there's a joke video there you can see, but it's this is a very traditional kind of spreading. I mean, lots of biological plants spread like this and so on. Of course, you have rivers and things that change the story, animals moving around. Diseases in people, though, used to spread like this. But of course, now we fly ourselves in these magic tubes, right? Which is completely made up. I mean, you think of planes. Anyway, so we move ourselves around and we sneeze on each other and bad things can happen, right? We do other things with each other that make it even worse. Okay, so people are interesting, crazy things. That is the wrong one. So come back here. Huh, bad thing. All right, it doesn't work. Stop it. Okay. Okay. I'll show you this other one. It's kind of fun if I can get it to work. It's a little, yeah, I'm sorry.
U.S. elections are always close. The nation is shocked Tuesday night to see John McCain defeat Barack Obama by a single vote. We sure showed him what a comeback looks like.
So this is from a while ago.
Outrage as the New York Times revealed the identity of the particular nominee international reaction has been just as intense, even in some of the most remote locations. However, the odometer hasn't become a hero to a small sliver of the population.
I thank you for your service. I thank you for what you've done for the United States. That guy is a factor of fuel. It's also a piggy.
Coming up, how long until we knew brand? Experts say
Okay. So I know that's very political, but oh, there, contagious. Yeah, he's got a nice thing, right? It's a little light bulb with a, yeah, well done, very good. There's a super plug for him. I know that's political, and I don't want to, carry on about sides of things, but it's a good video. So the thing is, what you would do is you go to the website and you put in your friend's name, and it makes the little video, and it puts in your name. So Deepak Chopra was the joke name, right? So so your friend's name is all through it, in all those different photos. Very clever. So it spread really well because it had that. So jokes spread, like good jokes will spread well. They're a great example of things because you get a payoff for making someone laugh. You enjoy that, and you enjoy laughing, right? So if it's a really good joke, right, a really good joke to take off, then you're willing to send it on. So that obviously the world is full of terrible jokes that never go anywhere, right? We don't measure those, but the ones that really spread all over the place, and whatever it's hashtag Save Big Bird or something. But this was pretty clever, and it had this element of, and we'll come back to this in social contagion, of, it has to get away from the originator, eventually. And for something to spread really well, it has to have something that average people want to pass on to other average people, right? So this is sort of against this idea of there being these key influentials that control the whole world by being the people. It's true that Oprah, Oprah tells you to buy a book, then you probably buy it. That's a different, she's not a normal person, right? She's magnified by media in an extraordinary way. So that's a whole other story. But for things to spread in this nice way through populations, word of mouth, there has to be something about the message eventually that makes you want to pass it on. So that was it was cleverly done, because you get the person's name all through it and they'd feel a little scared. Right, but it was one vote. That was the joke. So of course that went out, the week before, right? So. Okay. Australian politics, by the way, are great. Nothing ever bad happens in Australia. So let's see. So crazy people. Yeah, one time, about 20 years ago, there was Paul Keating got up, and the opposition, he was the prime minister, the opposition, and his party was just destroyed, right? They were going to lose the election. The opposition, for some reason, actually started to say something. They shouldn't have said anything. All they had to do was just turn up and just say, because right, the other team was gone. And so they did. So they had this thing, they called it the Fight Back package, and they had this whole thing, and they started to go on about it. So it gave them a chance, the people who were in charge, to really attack that and put all the focus on that. So he gets up in Parliament, and instead of using the word package, instead of using the word parrot, he went through the whole Monty Python sketch about dead parrots and put package in everywhere. And this can happen in the Australian or the English Parliament. And he just went, and everyone, this side's going berserk, and this side thinks it's hilarious, and they just do it. Anyway, it's ridiculous. So it's kind of like kindergarten. Like further away from kindergarten, lower. All right, so a couple of different types of contagion that we will be very roughly talking about. Infectious disease. So all these sorts of things, and they have lots of different properties, right? They can be incubated for very, very long times. They can be, the sneaky diseases that have kind of won out, if you like, are the ones that you get sick, but you don't know it, and you pass it on. I mean, they're the, right? If you have a disease that makes you, so Ebola in a way is a horrible thing, but it burns itself out pretty quickly. It would be bad to put that in Paris, the Upper West Side. So social contagion, lots of things. I mean, fantastic things spread socially. Fantastic things, right? Enormously. And they spread in different ways. We'll look at a very stylized kind of way of spreading, this threshold model type stuff, and see that has all sorts of interesting behaviors that are very, very different to what we might think of as simple disease type spreading. All right, so that's the focus of this set of slides, and then we'll move on to social contagion. All right, so very simple background story for disease spreading. So this goes back to the 20s. The first models were simple differential equation type models. So it's known as not very beautifully as the SIR model. Some of you will have heard of this, of course, but it's a very elementary model of disease contagion. So these three states: S for susceptible, I for infective or infectious, right? So there's you're in a state where you can infect others, and R is recovered or removed or refractory, right? Which is, you know, a nice way of saying dead, or recovered, and so there's also the possibility that you could be infected again, right? Yeah. Usually I have to say that people maybe in math, people do say they use words that are a little too strong, like, you know, like annihilation operators in, I mean, I guess it does in physics, you know, there's these things you're like, really? You know, so didn't get picked on the football team, obviously. So trying to put it into your math. Anyway, so channeling the anger, it's good. Let's see, so simple thing, we're going to have some population and we're going to address this problem. What's the population, right? So we're just going to have some population which is sort of n, and we'll divide by n, and then we'll just think about, well, what's the fraction of this population that's infected, what's the fraction that's recovered, and so on. So they should add up to 1, so that's good. There is the zombie model, right? So zombies, this is a Z, yeah, or a Z. It's a Z in there. It's a little more complicated, but that's had some fun. Let's see, so this original model, and this is not obvious when you look at it because, you know, it's fun, there are fun equations and so on. It presumes random interactions, right? It's sometimes called the mass action principle. So if you're susceptible, and there are two ways to think about it. One is a discrete, where there actually are individuals bumping around in this big vat. Another is more of this continuous model where you have differential equations pop out, and you have you know, fractions of individuals, and you sort of think of them as being, you don't actually have separate individuals in your model, you just think about that as happening. You talk about the probabilities of these individuals bumping into each other. In fact, you really think about an infinite population. So you have this vat of things, humans or bats or whatever they are, and they're bumping into each other, and the interactions are completely random, they're independent, and there's no memory, right? So I should say for an individual, if you imagine there, so if you bump into someone, they sneeze on you, you say good, go away, and then the next one sneezes on you, and the next one, so you forget about all the previous sneezes, which of course doesn't happen with normal immune response, where you get some, actually, you know, if it's working well, you in fact start to build up some immunity, right, to what's happening. That's really sort of the opposite of what can happen with, potentially with social contagion. Right? Social contagion, both of those things can happen. You see something you don't like and you sort of put a little reinforcement up, so it could be a bit like that. Or, you know, because you start seeing it so many times, you actually, in fact, will eventually adopt it. Especially if you see it from, you know, disparate sources, and, yeah, or at least perceived disparate sources. So there's discrete and continuous time versions. I just want to go through the very basics of these things and talk about one of the most important quantities in here, which is this reproduction number. Very simple idea, right? So if someone gets infected, they're in some population, what's the typical number of individuals they infect, right, before they recover, say, if they can recover. So what we'll look at there is that this number comes out of these random interaction models, and it's just one number. So people, this is a big failing we have. People like to characterize a system with one number, right? We really like to do that. So we'll do it with weather. You know, here's the effective temperature. You know, we'll try and roll the other things in, humidity, and right. And it's actually not what you should do. Some systems you need to know these three numbers, and you figure out this is the most important one, and here are the 4 secondary ones, and here are 10 tertiary ones. So that's how you should characterize. I mean, you're flying a plane, you don't want one number in front of you, which is like flying, not flying, right? Which is some sum of all of these other instruments in front of you. We figured out that would be a bad plan, but we sort of have this idea that would be great for society. Let's have one number. Let's have one number. Or, you know, whatever it is we're trying to measure. Because someone further up the chain just wants to see, like, there's a number here, and that whole thing is good. OK, so that's going to pop out of this stuff. So here's a little discrete time automata. So we have these subpopulations here, and there's a clock, right? And they're running into each other. And so we have all these little parameters in here. So there's these transition probabilities. So beta is going to be the probability for an infected, for a susceptible becoming infected, given they ran into an individual who's infected. So that means that the probability of becoming a susceptible becoming infected is beta times I, right? So these quantities are fractions that add up to each other. Or actually, right, they're numbers. So you're susceptible, you randomly interact with someone else, there's a probability S that that person is susceptible. You know, it's a big population, so you don't matter in this. I is the probability that you run into someone who's infected, and R is someone who's recovered. So these don't matter. If you run into someone who's infected, then there's a probability that sneeze, or whatever else transmission you have, is effective, and you become an infected yourself. So in the simplest version of all of this, you have that story. Then you have something that's the infected is just independent of everything else, have a probability of recovering, and that's R, and they have a probability of staying in their same state, right? 1 minus R. And then, depending on the way you set this up, you may or may not have this transition, right? So you could be a recovered who becomes susceptible again. So for some diseases, that can make sense. For some, right, there's a period of immunity you have, and then you're sick again. It can happen for social contagion too, right? So maybe you love watching, I don't know, some kind of class of movies or TV shows for a while, and then you're done with it. You're done with it, and then after a while, you're like, oh, you know, I could watch horror movies again, right? So, or diets or anything, right? So or religion. It doesn't mean you go back to the same one. It could be a state where you're kind of not in that category. So that's plausible. So this cycling is what I'm trying to say is plausible, right? Okay. Something like chickenpox, then that's the plan is you end up here and you can't get it again, but you can get shingles, right? So you couple into some other bad thing over here. Yeah. Of course, cleverly I don't really like this, but we created a vaccine for chickenpox. So we have to see how that plays out. You guys, because you're all 3 years old, probably had that. But it's a funny thing, right? It may work for our whole lives, or it may not, right? So I don't know. It's not good to get chickenpox when you're older, is really the story. So we'll see. There's some economic element to that vaccine, right? Because people don't, the kids aren't sick, so you can stay home, right? It doesn't mess up everything. It's not a deadly disease, is the point.
Well, doesn't it also prevent shingles if you're older and had chickenpox, or am I wrong?
Chickenpox, if you get chickenpox.
Right, but does the
I don't know about the vaccine, no.
For some reason I had the impression that there is a shingles vaccine. Okay, maybe that's what I'm thinking about.
Yeah. Right, so it's good not to, There's a South Park cartoon about getting your kids to have the horrible diseases that others have, like chickenpox. Yeah. Obviously Kenny dies, but but just trying to do the right thing. Okay. I don't know if I can advocate that. But anyway, after recovery, that showed, but I guess I did. Could get in trouble. So let's see. So loss of immunity is rho. So we have these three transition probabilities. So this is now a matrix story, okay, if you want to write down the transition. Well, it's a complicated matrix. So the original models, it's not published, but Reed and Frost wrote about this back in the 20s. You have these 3 papers, which you could get to if you want, just talking about it's a differential equation model. This is back in, again, back in the 20s and 30s, right? Yep. And so I'll show you what this looks like. It's a nice model. So now these things are rates, these quantities are rates. But so the rate of change of the susceptibles, there's some decrease because some so this is the interaction term between the infecteds and the susceptibles, right? So that's they're mixing. There's some rate then that they transform the susceptibles out. There are some recovereds that are becoming susceptible again with this rate, so they're popping up. So there's this term and this term balance here, this term and this term balance here, and DIDT, you're losing some infecteds that become recovered. So if you add up all of this, right? Everything cancels out on the right-hand side. We get 0. And that is d by dt of the s plus I plus r, which is the total population, which is 1. So that doesn't change. It's really an upsetting noise. I don't know. OK, so fair enough. All right, so these are rates. Right, so something that's hiding in both of these is, or can be extracted from both of these setups. And I guess I have slides for this. But so it's this so-called reproduction number, R0. I'm going to say 0. R0 if you like, but R0. 0 doesn't get used enough. All right. Epidemic threshold. If R0 is greater than 1, an epidemic takes off. Right? So what's happening is this is the expected number or the average number. So you get infected, you're in your population. This is the average number of new infectives you create early on, right? So once it's saturated, we're done. But you imagine you have a little seed in this network, in this system. So if you infect on average 2 people, right? They have 2 people that they infect on average, and they infect, right? So it's exponential growth early on. So that's the simplest outcome of these. That's the simple story that comes out of these models, is that there is this exponential growth if it's successful. If R0 is less than 1 on average, so maybe you get 1 person, but so the average is 0.8, right? So maybe you get 2 people, 3 people, but on average, it's going to peter out. It's going to die away, right? My name shouldn't be like that. OK, so fair enough. Very simple story. OK, all right. So let's get that out of this. Out of these setups. So we have 1 infective, right? We have this pool of, they're all susceptibles, they're all happy, and we put in Ebola. Okay. And that's happened from some other reason. So we have this time t equals 0, we have this single infective is going to bump into a susceptible. This is just a simple little bit of math here, it's good. And they have this probability transition of beta. Okay. Time t equals 1, this infective remains infected, that first person. So we want to see how many people that first person gets. And then we can just use that again and again. Because it's random, you never bump into the same people twice, right? It's a big enough population, you can assume that early on. So 1 minus r is probably that this initial infective stays infected. Time t equals k, and there's always this probability beta of infecting someone. They always get 1 chance. Time t equals k, they're still infected with this probability, 1 minus r to the k. So this is a nice little exponential decay. Okay. Yep. That number is less than 1, of course. It's a probability, so it's 1 minus r to the k is equal to e to the k ln of 1 minus r. Right, we just do the sneaky thing. E to the ln of 1 minus r is this thing. And because this number is less than 1, log of something less than 1 is negative, so it is a nice thing to do to say, make it inherently positive. Right, so this quantity in here now is greater than 1, so this is a positive number, it's minus k, so it's decaying exponentially. Right. Random failure, exponentials. Oh my God, I need back surgery. OK. So we can put all this together and we'll say, what's the expected number that you infect? So there was probably beta of infected someone in the first go at t equals 0. You have to, the initial infected has to stay infected. Then they have another chance, stay infected again, blah, blah, blah. OK? So we just sum that out. So it's the expected number. Of course, there's a beta. We pull this guy out. Geometric sum. Very nice, right? Delicious. OK. So this is 1 plus a squared plus a cubed. Yeah? So it's 1 over 1 minus a, which is 1 over 1 minus r. These guys cancel. We get 1 over r. So it's beta over r. So this is quite a nice thing. So this is this expected number of infectives that the first one generates is the ratio of the infection rate and over the recovery rate. So that's pretty good. So if those things are balanced, sorry, probability, they're probabilities here. So if these things are balanced, then whatever they are, half and a half or a quarter, if they're balanced, then we're at that threshold, right? So if that balance just goes out a little way, then we start to get a chance of things taking off. Right? So this just comes out of a simple model. Very nice. This idea of, the question is, does this thing take off or not? right? And if you have some, if you have something a little more, a little variation. So you have S0 in official. So there are some that are immune. There's some fraction S0 to start with that are actually susceptible. Then you have to put that in there as well. You get that piece as well. Okay, so it reduces it slightly. Fair enough. All right, let's do it for the other one, and we'll get to the sort of the big kind of outcome of this. It's a pretty simple story, and we'll see where it goes. Sort of, I'll try to say in the last few minutes where it goes wrong, because you can see the game would be: here's one number that describes this thing, measles, whatever it is. Let's get that number below 1. Let's do whatever we need to do to get. Which is, in principle, what that means is you go out and vaccinate people if you figured out how to do that. Right, you quarantine or whatever it is, you do something to do that to fix it up. But it becomes it's not enough once you go to where we are now with all this travel and so on, because you have to think about how people move around and the disease separately. Right, they're two different parts of this. What's human mobility like, which of course is something we're understanding more and more recently in very detailed ways, and what is the disease itself like. So we had that the second equation in there was a ddt of the infected. I'm sorry, this is just sort of Helvetica, but right, there's a beta SI, so this is now a rate. This is the product of the susceptibles and the infective, and then there was some rate at which they vanish. So the infecteds are growing with this piece, susceptibles are becoming infecteds, and some of them are recovering. There's an I just sitting there, so we can pull this out and just analyze this pretty simply. You can solve these equations in very nice ways, but this is enough for us. So we just have beta s minus r times I. And if we think about initially, right, most of them are susceptible. We could have this set up where we have some immunes, but so s is almost 1. But initially, things are going to grow. This is going to be, we need this to be greater than 0, right? di dt has to be some quantity times I. It's going to grow exponentially, right? This quantity, just an approximate thing. If this quantity is greater than 0, then we have di dt equals some positive number times I, which if you solve that, if this was, there's susceptibles in here which are changing, but if we just had a constant here, that's exponential growth, right? And if it's negative, they're dying away. So we need that. So if we set time equal to 0, then we'd want this story. Beta s0 times minus r is greater than 0. And so we have this piece, and this is then the same structure. Now these are rates, but we have exactly the same story as we had before, right? But these are different kinds of quantities. Before there were probabilities, now they're rates. I guess that was naughty of me to use the same notation. But anyway, so it's the same story, and we're gonna call this beast. Sorry, we're gonna call this quantity R0 again. Maybe I could write that. Yeah. So it's a simple but very fundamental story. So I want to sort of labor on this base a little bit, I suppose. But does this make sense? It's elementary kind of algebra really, but this is what you get. So if you have if R0 is tunable, and that could be tuning, as we see now, beta and R, these two probabilities or rates, they could be tuned independently, but their fraction being tuned will give you this. So this is the output of one of these models, very simple. We're dialing one of these things. So the final fraction that are infected, and so this is 1, so this is very, very bad, is 0 up until 1, right? Which is the story I was saying. I mean, it's clear from these equations. But this is the thing. So yes, all right, so you're in this world, and if the disease takes off, then we're in trouble. What you want to do is somehow shift conditions so that you're on this side of what is a beautiful phase transition, right? So there's a continuous phase transition. We see this in all sorts of systems. And so it's a very appealing kind of story, right? It's a big public problem, big public health problem, big just fundamental human problem. And biology, I mean, we're worried about animals having the same things, happen to them, whatever it is. Trees, bad things spread through trees, and koalas get sick, and Tasmanian devils, that's not good. They have a contagious form of cancer, which is unbelievable. Poor little guys. They're really, really cute, actually. They're about this big. And they do eat anything of really any size. They have incredibly strong jaws, but they wait till they're dead. All right. Clever little carnivore. OK, so it's a great idea from a simple model, right? Great idea from a simple model. Fantastic. They do not twirl in circles. OK. So there are many variants of this model. You can imagine we could go all over the place. As I said, I talked about SIRS, but you might say SIS. They just become infected, then they're straight back into susceptible. There's this cycle where you have the recovered state as well. There are compartment models where you segregate the population by age and gender and so on, different categories. There's exposed, right? So you could be exposed to the disease for a while. So this is where, and you might be, there are complicated things, right? So in this piece, you might be infectious. Now you're showing the symptoms, so no one goes near you, because you're horribly, horribly diseased. Yeah, I always think the bless you thing could have that. It could be bless you because I want you to be better, but really it's about me because I don't want you to have a horrible disease. So it's kind of amusing. Get that devil out of you. And right, so over long periods of time, there's people moving around. So you can put all these things in there. A lot of the models, though, until I would say recently, have still had this big random mixing story. And that's OK at a small scale, for sure. Right? There's random mixing that goes along in universities and businesses and schools and so on, where people are interacting kind of approximately in a random kind of way. But it's much more complicated as we move up. So I'll just leave you with this, I think. So here's a great problem, right? So we do this with earthquakes. We're very worried about those sorts of things. We're worried about all sorts of calamitous pieces. Can we predict? Can we tell that something's taking off? Can we predict the size of it? Can we predict when it's spreading? And then perhaps jump on it. So how important is this number R0, right? So measles, there are all sorts of characterizations of R0 after the fact of something spreading. So you can see that's problematic, right? So something spreads, and you look at it, what its exponential takeoff was, and you get some estimate. And I'm really not kidding when I say that in science a few years ago, there were 2 estimates of R0 for SARS, right? That came up with about 2. 2 is bad. 10 is really bad, but 2 is bad. And they were essentially, one of them basically did this. It drew sort of the model was an exponential takeoff model and really fit it like this. That's not good. And you can't really think of Hong Kong as a randomly mixing environment. Right. So, so these are some estimates of R0, obviously post hoc. And estimates for these things, maybe 2 or 3. It's about the same for all of these. Spanish flu, so 500,000 people there, 70,000 people in the US. For Asia, the so-called Asian flu is 57, 58. This was terrible. I mean, there was many more worldwide, of course. But trying to at least keep it in some well-defined thing. Of course, the population size has changed tremendously. They're very different. So, but they all have the same R0, is what I'm trying to say. Very different outcomes. So can we kind of understand that? Because it does not happen in these simple models. All of them have the same outcome. Right? There might be, and I'll come back to this, there might be that the thing just sputters out straight away, right? The first person just fails to infect anyone else. But if it does take off, there is a characteristic size that you always get to, because they're random mixing models. There's no other chance in there. And SARS, and I think this is a correct estimate, but on the order of 1,000, right? I mean, there's a massive reaction to that as well. So you have to, of course, start to factor in how people react and how states and governments and so on react. Or Toronto was a good example there, where they had a SARS outbreak, and then they said, no, it's all under control, and then they had more, and then it began, no one's going to visit Toronto, right? It was a disaster. Yeah. So they're trying to manage it, but because it hurts if people don't visit. So, all right, so we know about this. These power law size distributions are important everywhere else. We've talked about these things. They're all there, popularity. What about epidemics? Well, it turns out, we love these things and these heavy tail distributions. They're all over the place, but they don't have to be. And so what about epidemics? And it turns out there hasn't been much on this, and that's what we'll start with next Tuesday. And of course, data is not so good for this, but we'll get somewhere with it. All right. Turns out Iceland is a terrific little Petri dish. And good at recording what happens in its Petri dish for like 100 years. Okay, people, you are free to escape.